Hello everyone. Welcome to a incredible project. Took me a lot of time. A lot of mistakes were made, but there was a lot of learning there too. This is canister Damascus, made of ball bearings. So, ball bearings, metal powder, heated up to about 2300 degrees and compressed. So, the term canister refers to the container it sits in. So, you can see here I'm cutting a piece of 3-inch by 3-inch square tubing. I believe this has an eighth of an inch wall thickness, and it is about 5 inches long. So you'll see here, pops free. Take some measurements here, show you, I guess across the pond, this would be 75 millimeter tube. Square tubing would be 125 millimeters long, something like that. It'd be 3 millimeters wall thickness. I think that's right. Anyway, so this is a rather tedious process, but I've done quite a few different types of canister Damascus, and the ball bearing ones are pretty. They're easier now. The learning curve is pretty steep for these if you don't do the steps quite perfect, and a lot of attention to detail. You can have the final billet when it's done will fail very easily or crack or it won't be homogeneous. So it's but I'll take you through the steps here, step by step. So here's a 3-inch square tubing, 5 inches long. Okay, cut a section of that off, and then I have to make some end caps. So, but before I do that, I'm going to paint it. A lot of people use whiteout, and I use white spray paint. Now, if you get the material safety data sheet, the MSDS for this type of paint, the main component in white paint is titanium dioxide. Titanium dioxide is a very prevalent colorant to use in all types of paints. Anyway, so it's a principal component of this type of paint. And when you paint the inside, it leaves a coating of this titanium dioxide. It prevents the can from fusing, or the canister from fusing to whatever you put inside of it. So you can cut the can off later on. Here I am cutting out my end caps. I'm using some 3/16 plate for my end caps. I cut them out of my CNC plasma cutter. So here I'm going to weld with one end on the end of the canister. So you lose a little bit of length here. You see, I don't put the end cap on top of the tube. It sits within it. So you see I'm using my magnets to hold that flush, and I tack this in place, and then I weld all the way around. Now, you you want a completely airtight seal. You can't have oxygen get in and contaminate. Oxygen is the enemy. Whenever you're doing forge welding, you're going to be using flux, or you're going to be doing a zero atmosphere weld like with this canister. You can't let oxygen in. Now, there is a buildup of some air pressure that can occur, so you do have to have a way for the tube to vent, or else sometimes the tube can burst. And with a bunch of fine metal powder inside, that's at around 2200 degrees. If the can bursts, that can be dangerous. And so I've seen it happen. It just sprays out this glowing powdered steel, and then it actually burns even more rapidly once it comes out of the can because it hits a more oxygen, higher oxygen content environment, and they really start burning. And the metal powder I'm going to be using is very fine. It's like a talcum powder. It's actually an inhalation hazard. You got to be really careful when you're using it. So I'm going to weld up this edge 100%. Okay, and then you can see how everything's painted inside. Now I'm gonna in a series of stages, I'm gonna put in my different types of ball bearings. Here you'll see this, but I paint this end cap. Now the end caps are painted, and that helps it. You'll see when it comes to separate the can, it separates very easily. White paint is incredibly effective. Prevents the steel can from bonding. That square tube prevents it from from fusing to your interior, whatever metal you put inside of it. So I have a bunch of different ball bearings here. Some of these ball bearings are 1/2 inch in diameter, and some of them are 3/4. And then I have a bunch of 1/8 of an inch ball bearings here. And then I have some slightly smaller bearings that are just 3/16. So I have some 1/8 of an inch, some 3/16, some 1/2 inch, and some 3/4. So I'm going for a variegated look here. And so you'll see this pattern came out just exceptional. Here's the powder. I got it from Jantz. Bought it online. It's 1080 powder, 1080 steel with 4% nickel. So that's going to give me my bright. That's going to stay shiny after I put it in the acid, and so that's going to give me my etch. Now, all these ball bearings are not the same composition. Some of them are 52-100. Some of them are some different types of steels. So they will turn different shades. Some of these bearings get very dark after they're etched. Some of them only get a gray, and then the nickel powder. So here I'm using acetone. You got to clean these off. These are relatively clean when I got them. There's always a residue or grease, and any type of oil or grease or contaminant, that is the enemy of getting fusion. So especially if it was inside the can and that oil couldn't burn off. To be honest with you, I'm not sure exactly what type of what that would actually do inside the canister if you had residue inside the canister. But I'm going to be getting this at 2300 degrees, a little over 2300 actually. I'm shooting for 2350 when I do canister to Damascus. That's in degrees Fahrenheit. So I wipe these all down with acetone. It's a little tedious process. I place each one in by hand, and then I dump in some of the smaller bearings, and then I dump in some powder. Now, the reason for this, I've tried, you can't just dump in the larger particles, and you tap the sides of the can. You agitate it a little bit, and some people use a vibratory process to kind of settle and consolidate. You want that to be totally solid inside the can. The problem with that is these different size components, the different bearing sizes and the powder, they will self-stratify. If you're just not careful how you place them inside the can as you go, you'll end up with strata, like a layer of this, a layer of that, a layer of this. And so our goal is not to have that stratification of layers. We want this to kind of be mixed. I want to see, the other small butt bearings in between the bigger bearings, and then I want to see the metal powder. If you see here, I'm kind of placing them in one at a time, and once I get enough height of these bigger bearings built up, then I drop in the smaller bearings, and then I drop in some metal powder a little bit, and I'm kind of selectively moving that around and tapping it. So, and that might accommodate for some of the length of this video. A lot of it is me, and I edited this down quite a bit, guys. I didn't show you the whole process, but basically, I clean these down. I'm dumping the smaller bearings in, and you got to be careful. Those bearings will bounce right out of that tube if you dump them in too aggressively. They'll just dump it right out. But anyway, so I get in some of the larger bearings, and then I pour in these little ones, okay, and then I put in a little bit of metal powder, and so that's kind of the process. And then I kind of do another little progression of that, and then I do another little progression of that, and I just keep working my way up. And that's how it's kind of, I hate saying this, homogeneous. It's not homogeneous because it's a bunch of particles, but how about this? The distribution is uniform. Maybe that's a more accurate way of describing it. So I don't have just like a layer of these large balls and then a layer of the smaller bearings and then a layer of just nickel powder. I want it to be kind of uniform. I want to see, the balls obviously are big enough. They create a big enough surface in between each other. These bearings are a big enough diameter, so the smaller bearings fill up that space pretty easily. So this this type of, the half inch to 5/8 and 3/4 bearings with the eighth and the 3/16 bearings are almost the perfect distribution. I could have gone with a little bit bigger, smaller bearings, but this size proportion you guys see here works out extremely well for the pattern that I'm trying to achieve. And so, and here you see I'm getting to a point now where I'm dumping in some metal powder, and I'm kind of selectively looking down. It's not really precise. It's not imprecise either. But I'm kind of watching what I'm doing and making sure that these are evenly distributed. There's not a concentration of metal powder over here or over there. So you usually got to get all the bearings in first. And once they're kind of in position, then you can dump the powder in, tap the sides, and the powder will settle throughout. Now, when you're done with this whole process, as you fill up this tube, and you weld the end cap in, I usually fill the last little layer with just full powder, whatever it takes just to make an even layer, and then I can actually compress that end cap. And so you can see here that needs a bunch of powder. I haven't, but I'm making sure the balls get, the smaller bearings get above a certain point before I start dumping in powder. But I can actually take that end cap once I'm done and compress it against the powder. So when this is done properly, guys, you'll shake that can, you won't hear anything. No movement. No, the bearings, you can tap on it, it feels solid, right? Even though it's a bunch of bearings and some powder, but you have to get it compressed. You don't want oxygen in there. You don't want any contaminants in there. And so, as a matter of fact, you have to be careful when you're doing some of the initial forging. If you get too aggressive, in a stretching motion, there's these fissures that can develop on the outside corners, because that's where a lot of the stress gets concentrated in the initial stretching. And if it's not totally fused, you'll get these little fissures right on the corner. And this is after you extract the billet out of the can. And those, they form these little stress risers, and cracks propagate off of them, and it's next to impossible to save. So I've seen it where you can kind of try and flux it up and reforge it later if those fissures happen, but the best way to do this is to make sure this can is fully consolidated. There's no loose gaps anywhere in there. And then obviously I have to let it soak at a sufficient heat, and I don't get too aggressive with stretching the billet until I feel it's properly fused. And you can feel that. The first 2 or 3 squeezes on this, you can feel how malleable it is, or how it's not homogeneous, right? It's just loose material. You can feel that. But after like 3 or 4 good presses in the hydraulic press, you can feel it solidify. And you can see the resistance. The first few squeezes, it gives just really easily. After 2 or 3 squeezes, you can almost see there's a resistance to it. So it fuses pretty quickly, especially if you use the proper dies. Now I have a set of square dies I use for the initial drawing of this. And there's some different ways to do it now. I weld a handle onto this can, okay? But the handle itself prevents you from squeezing it in the length. I can't put that in my press and squeeze it. So when you use a handle like this, you're limited to just the pressure in the two, XY planes or whatever you want to call it. But I have done these where I don't weld a handle on it, and you have to use a set of pinchers to kind of move it around and get it, and the handle makes it easier. So here I am, I'm almost on optimal temp. I'm shooting for 2350. I was having a little hard time regulating my temperature in my forge today, and I'm running these Venturi burners. They can be finicky, but I was above 2300, 2350, even 2400 would be okay, but sometimes there's a grain growth that can occur, and you can actually forge as low as 2200. It's better. It depends on the steel. Certain steels are very finicky. You can overheat them. The grain structure grows, and you can ruin it actually. But That's not the case with this steel I'm using. It's mostly 5100 and then 1080 powder. This is the first squeeze. Now look, guys, got my squaring dies, and I'm running this, and I'm not getting crazy. And this press is rated for 40 tons, and so I'm barely squeezing this. And you can see the first few squeezes, it gives a lot. So you got to be careful. The first few presses you do, you have to be careful, and you're just giving it a little squeeze, rotating it, giving it a little squeeze, rotating, giving it a little squeeze. If you really squeeze that, it will lengthen and draw out, and then the corners, which aren't fully confused yet, will split, and you'll have these splits on those outside corners once you cut that can open and extract that piece, and those cracks will propagate right off those corners, and you might as well just start over at that point. Especially if oxygen gets in there and oxygenates it, or sorry, not oxygenates it, it reacts and builds up scale. If it reacts with that oxygen in those, it's really hard to get that clean, and you can try and grind it out and reflux it and reforge it. It's best just to do it right from the beginning. And so now look at this. Now you can already see this is getting very solid. Look at how much more resistant it is to those, to the pressing operation. And just, I don't know how many presses that was. Now, so I can feel now it's getting more solid. I can get a little more aggressive once I know it's kind of fused. Now I let this soak. It was in the forge. I edited that out, but you gotta let these soak in the forge. You gotta make sure that all that material is fully heated throughout at the proper temperature. So I'm looking for at least 2300 all the way through there. Now, there is some deceptive optical things that occur. So once you really start squeezing this, because of the paint on the inside of that steel can is not sticking to the interior, okay? So you can see all kinds of weird things. You'll see it looks like the billet is too cool. You'll see these cold spots. They look very dark. You'll see a cold spot, and it's deceptive. That normally in a billet you'd be like, okay, that's too cold. I got to put it back in the furnace and heat it, but that's not the case. The interior mass, the main mass I'm working inside that can, actually is way hotter, because what happens is as it separates from the can a little bit, there's a little bit of a gap inside, and so when that happens, that exterior can cools rapidly, and it'll show up. It looks black, right, or a dull red, but inside that canister, it is. Maybe you see some pictures. I never try and cut open the can when it's still hot, but I did one where I had to get it open for some reason to look at something had failed in the pressing operation, and the can looked like room temperature, but when you cut it open, the billet was glowing inside. So when something has that much mass, it retains that heat, right? So here's my second heat on this. Now look at this. I'm getting way more aggressive here. I got the temp a little higher. I let it soak really good at that temperature. And so you can see some of that can turns red, turns a dull red, and that's not an indication of the temperature. Inside that can, that metal is at least 2250 to 2300 degrees. But the outside of the can goes into red or orange phase, and then you'll even see it get red. But that inside of that can is orange. And so it's at a good, yellow. It's at a yellow heat. And here I'm switching to my smaller dies. I'm starting to work this piece down. And so this is, and in one of these heats you'll see here, I should have thrown it back in the fire sooner. I get kind of a target fixation when I start doing some of these pressing operations, and sometimes I work it past its workability. Right, the piece is cooling off too much, and my press is so powerful that sometimes I just keep going. It's probably not good for the press, but this press is so overbuilt. I don't. There is a small flexural issue I was getting, and I might actually put some steel braces on the. This is a C frame press for the C shape, right? And so I might convert it into an H frame here in the future. You might actually see some shots later on in the video. I did beef up this press because I'm starting to run it at higher some of the forging operations I'm doing, I'm running over 25 tons. I'm running at 30 or 35 tons. And so that's where I wanted to run at with this PSI, higher PSI in this hydraulic system. So I'm raising the tonnage. So I think I did in one of these subsequent shots. You'll see that I did add some raising to that press. But here's another subsequent heat. Now I've switched out my squaring dies, okay, and I'm running my combo dies. And I don't use the drawing dies, the round ones. I'm just using the flat dies here. And you can see this piece is completely consolidated. I'm just drawing it out now. That's it. It's I could feel it as I'm pressing this, and I can physically or visually observe it, and it is being how it's behaving under the hammer when it's contacting it, under the press, excuse me. And this I can tell, and I can, there's a lot of visual indicators. So now I'm just drawing it out. It's fused. It's homogeneous. All the bearing in the metal powder has been heated sufficiently, put under enough pressing operations where it's homogeneous. Now I'm just drawing it out. And so you'll see here I'm drawing this out. Now the can is still on this. And you'll notice, a more astute person that's done this, you may look at this and be like, hey, Ben, that metal looks like it's cooler than it should be, right? You should throw that back in the furnace. But check this out. Some of the can starts splitting open here. You can see little fractures in the can. That's fine. I'm not concerned about oxygen getting in at this point, right? It's fused. So look inside that can, guys. You'll see some fissures. Look at that. That's orange. Or I'm sorry, that's yellow. It's a yellow heat inside that can. So that can looks, visually, just, superficially, you're looking at this, you're like, hey, that's way too cold, man. Throw that back in the furnace. But that's not the case. That's just the canister. If you look inside those fissures, it's yellow in there. I got that thing at a good 22 to 2300. Inside those cracks, you can see it's much hotter. And that's a good indication when you're working with a canister, right? That means it hasn't fused. It's going to be very easy to get off. You run an angle grinder with a cutoff disc vertically down a couple of corners, and the thing just basically falls off. No grinding the can off or none of that. It works really well. And in fact, you can use a certain amount of pressing operations to actually induce that so that it does fall off easier. And here you can see that. So I'm just going to throw that in there off to the side. I'm going to let it cool so I can cut that can off. So here's some shots of the can, and you'll see the can came right off. So easy, like no joke. 2 vertical cuts, it literally just dropped out, and that is perfect. That white paint is just outstanding in that capacity. So this is the first etch, guys. Now check out this end grain. This turned out really nice. I've just extracted this billet out of that can. I've done a light grind. Okay, this is the side. Now the side's it's going to be more elongated. All those little things are stretched out. The small ones and the larger bearings are stretched out. But that's what it looks like on the side. Now take a look on the end grain. This is what I was going for. I can't tell you how excited I was. This was the exact pattern I was going for. Okay, the larger bearings with some of the smaller, different sizes. I had 2 different sizes, smaller bearings, and then the nickel powder. So that's exactly what I was going for, and there was no big inclusions or failures or cracks. I couldn't be happier with this. Now, I did include a mistake I made in this later on, but I'll talk about that later. But so. This is a little dip. Now, I do have a legitimate ferric chloride tank, guys. I apologize for the little Tupperware thing. I can easily modify my concentration in this small little dish. So I can put water in it and dilute it if I want a weaker solution, or I can change it. So I don't mess a lot with my main tank I have a 6-inch diameter PVC canister I use that I keep ferrochloride in. But this little one is good for test etches, and I don't care if it gets dirty or gets, you know, dirt in it or whatever. So there is the side grain, which is really interesting, and you can see how that's been stretched out. But where the cross section is on the end, take a look at the end cut here. Um, that's the pattern I want on the sides of this billet. So to be honest with you, I haven't even decided what I'm going to make. Hey, look at that. Oh my gosh, I am so happy. This is just incredible. So, um, I, you know, I must have stared at this for 15 minutes. It's just stoked. Sometimes these things are so complex and all the different phases of it. And sometimes you got to do it enough. Once you do enough of these canisters, you can kind of get a guess on what the pattern will be like once you've done it enough and you've seen it. But this is a unique one. And I have some chain Damascus and some gear Damascus coming up in some subsequent videos I'll show you guys. But this one came out pretty good. So maybe leave me some suggestions. You guys want me to make a knife out of this stuff? I really don't know. A hammer? I don't know what I could make out of this stuff, but hit me up in the comment section. Tell me what you'd like me to make out of this stuff. Anyway, so there's the end grain. Okay, this is half the battle. Okay, now I'm going to transfer that to the sides. I want to see that pattern on the sides. So here what we're going to do. I'm going to make some even marks. Now this has to be planned out. You have to plan these cuts, and you have to plan this all because everything gets drawn out, right? And as you press these things, it distorts the pattern. So there needs to be some planning involved, or else you can start drawing this out and the pattern's really distorted, or it's drawn out so much the pattern is just really kind of just kind of nullified or kind of ruined, right? You can stretch something so much that it almost doesn't even really look like the original intention was. So I mark this off in a certain increment, right? Now I'm going to cut these. I'm going to cut these up. Then I'm going to rotate them, and I'm going to fuse them back together to get the patterns on the sides. And I don't show the cutting operation, but I just used an abrasive disc, cut these things off, and I was able to turn and restack them. Now, these welds are much more critical than a regular type of Damascus weld. It's just much more difficult to do. So, but I'll take you guys through it. Now look, I've cut these and I've rotated them. So I cut them, I've rotated them, and I've ground where they mate. You have to have that ground like perfectly smooth. And you'll see here, I'll show you some the grinding that I did on some of these sides. Look at that. This has to be perfectly flat, perfectly smooth. There's a little inclusions in that. I'm not that concerned about that. I'm going to get this back up to 2300, 2400 again and give it another press. But you have to get this ground perfectly smooth. You have to clean these with acetone, which I didn't show in the video here, but I cleaned them all with acetone. I clamped them together, and I'm going to tack these, right? I'm going to tack weld these up and get these all so they're not going to be able to move. Now, this is not good enough. You have to weld all the way around these seams. Any air gets in there and oxidizes, and they will not fuse. Now, there's a trick you can do. After you tack this, you could soak it in some kerosene, okay? And the kerosene will, through capillary action, flow into those small little voids or small little areas in between there. And then you take it right out of the kerosene dip and throw it right in your furnace. And the kerosene burns off, and then it leaves carbon in that little gap. And that carbon will actually help it. Once you get to a high enough temperature, it'll actually uptake. The metal will uptake the carbon, and it's actually beneficial in a lot of instances. The problem is, in certain types of patterning, like I'm going after, would leave a dark line. That carbon line would be present in there. You'd see that. So I'm not doing that. So I'm welding these all the way around and completely sealing them off. Anyway, so I'm getting back up to heat again, and I made a critical mistake here. So I have the welds on the sides. Now, this is the first press. Now check this out. I don't have a handle on it. I'm getting this up, and boom, I hit it. Now right now, after that squish, I'm using a lot of pressure. Look at that I'm reducing that height significantly. I'm putting a really good pressure on there, and that's probably fused now because I got it hot enough. But look at this. This is mistake number one. Now I turn it started bending a little bit from all the from the vertical squeeze, and so it started to curve a little bit. So this was a mistake. I should have stopped and ground the welds off. Okay, because what I just did right there, I got ahead of myself. I pressed those welds into the billet. This here, I turned it over on its side. I shouldn't have done this. I should have stopped and ground the welds off before I proceeded. Once it was fused, I should have ground those welds. Now I just pressed those welds into that. Now I did another heat. I'm doing another squeeze here. I got this fused, and I turn and hit it again on the sides here. But those sides, those welds I've just pressed in have contaminated that billet. They're going to show up. Now, it's not a big deal. You just have to grind it out a little bit. And the welds weren't really heavy welds, but I should have done a TIG welding process where it's autogenous, where I fuse it. There's no metal, but here it is, guys. This is it. Look at this. Oh my gosh. And I'm so OCD about the weld contamination, but they'll grind out. They're not that deep actually, but look at how beautiful. Got the distribution, the balance I was looking for, the variegation. It's all there. Now the last end one I actually turned. That was intentional because that's probably going to be a handle portion or something like that. But you can see I'm going to take this out in some natural light, guys. This came out beautiful. I reground this. I almost wanted to reshoot the etching operation so I didn't have those weld contaminations you see there. But I wanted to get this video uploaded. I wanted you guys to see it. But I have reground this and I ground a little deeper. There's no more welds. It's beautiful. This pattern just came out phenomenal. And here's a little bit of patterning, what the patterning looks on the sides. But you can see this pattern just came out incredible. It almost looks like the cross section of concrete that's been cut with the aggregate, or almost looks like a fruit cake or something. I really don't know with this pattern what I would name it if it needed a moniker, but I'm so pleased with it, except for those darn weld contaminations that got pressed back in the billet, but they ground out. And it's a beautiful. It came out, had perfect good fusion, no delams. It just came out incredible. And my temp control was iffy with my forge that day, but I think I got it dialed in. And anyway, guys, this was a longer video, guys, but I want to thank you so much. This means a lot to me, you guys watching this, and tell me what you want me to make out of this. And I really appreciate you guys. I want you guys to stay safe. Stay vigilant, and I'll see you guys later. Talk to you guys on the next one.